Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Or Dunkelman visiting us. He's going to speak to us on key recovery attacks of practical complexity on AES variants. Or is a postdoc at the Weizmann Institute and has been a postdoc at the École Normale Supérieure and at Leuven, something like that. So thank you for coming.
Thank you for having me. So this is a joint work with Alex Biryukov, Nathan Keller, Dmitry Khovratovich, and Adi Shamir. And I'm going to discuss key recovery attacks of practical complexity on AES variants. Now, AES is the advanced encryption standard, so just to get a rough estimation, how many of you know what the AES is? Heard of? Great, okay, so we can skip some of the things. It's always a problem when you go to a place and you don't know who you're going to meet there. So I will go very briefly over the concepts of the AES, why we thought it was secure, and then a bit about attacks on the AES. Now, cryptanalysis in recent years, especially symmetric key cryptanalysis, went towards a very theoretical approach. Now, when I say theoretical approach, I don't mean P versus NP sort of theoretical approach. I mean towards 2 to the 400th time complexity approach. Now, that prevents us to discuss things with either practical people who say that 2 to the 400 is a bit too much, and theoretical people who complain that order of 1 is order of 1 and nobody cares about it. So we're stuck somewhere in the middle, and we're trying actually to bridge a bit this problem of a very huge gap between what is considered practical and what is considered theoretical, because whenever I'm going to say in this talk theoretical, I mean practical theoretical, 2 to the 400. And when I say practical, I mean something which is practical. You can do it on your nearest, well, either grid or even your PC. So let's start with a very quick reminder what a block cipher is. So this is one of the most basic cryptographic algorithms. There was the data encryption standard that was standardized in 1975 or 7, depending how you count it, somewhere in between. So there is a symmetric key, which is shared between the two sides. And there is a transformation. Actually, a block cipher is a permutation, a keyed permutation that takes blocks of bits of n bits and generate usually the same size of the output. This is a sort of a bijection, not necessarily into the same space, because some block ciphers have additional functionality. But today, most of the time, we deal with block ciphers which take an n-bit block and return an n-bit block. So if you want to treat it formally, there is an n-bit plaintext, k-bit key, and it's just a transformation. Now, actually, when you encrypt data, you have more than that. So you have some mode of operation, a way to wrap around this block cipher, which can treat only a specific amount of data at each invocation. So there is a system behind the block cipher. And we have to remember that it's not out of the blue. Standing there, I mean, like there is this box and does whatever you want. You have to somehow communicate with it and make it give you the right inputs or the right functionality that you're looking for. Okay, so this is a very crash course at differential cryptanalysis. Differential cryptanalysis is a method to attack or cryptanalyze block ciphers. It was introduced in the 90s by BM and Shamir, and its basic idea is, instead of looking at a specific value and try to determine the key by looking at its decryption, you look at pairs. So you take two encryptions, P and P star, and then you look at the differences and how things behave. Now, the reason this is very good is because the differences have the tendency to propagate very nicely. For example, if you have a linear operation, the difference of the output is the linear transformation on the difference of the input. Now, this is really great because when I say linear, well, in cryptography, sometimes we mix linear and affine. So it also works for affine transformations, but the nice thing is that when you XOR a key, the difference before the XOR and after the XOR is the same. So the key disappears from the encryption algorithm. Of course, other things becomes a bit harder. For example, when you have nonlinear operations, they actually get very annoying when you try to analyze it, because when you have a nonlinear operation, you know the input difference, you do not necessarily know the output difference, besides the standard case where the input difference is 0. Assuming that your function is deterministic, which is most of the times, unless you're using Pentium 60 megahertz, the first generation, when you put the same input, you get the same output. Okay. So a quick introduction to the AES. So as I said before, as you probably know, it was designed by Vincent Rayman and Johan Diemen under the name Rayndale. It was submitted to the NIST competition in 1998. There was a very long process of selecting the AES. Many people tried to break it, and at the end it was selected. It has an SP network structure, I will show you in a second. Its block size is 128 bits, key size 128, 192, or 256. Now, most modern symmetric key ciphers operate in the concept of rounds. So you have some basic transformation, and then you repeat it. You iterate it again and again. In the case of AES, it's either 10, 12, or 14 rounds, depending on the key size. Okay. Questions so far? Great. So you put, this is the state. You take 16 bytes of the state, you put it in 4x4 matrix. Each round is composed of 4 simple operations. The first one is the subbytes operation, which is a nonlinear transformation, a table lookup if you like. A shift row operation, which takes each row and rotates it to the left by I bytes. So the first row is unrotated, the second one is rotated by 1 byte to the left, 2 bytes, 3 bytes to the left. Then the mixed columns operation, which takes each column and multiplies it by an MDS matrix. I will show you in a second. And then the add round key operation, which adds the subkey. Now, usually, as I told you before, there is a key which is used to generate many subkeys. The reason is that if you have a key of, let's say, 128 bits or 256 bits, then you have to generate enough keying material, subkey material, to affect the entire encryption. So there is also a subkey generation algorithm or key schedule algorithm which transforms this 256-bit key into 15 subkeys of 128 bits each. So here is the mixed column operation. You take 4 bytes and you multiply it by this very nice matrix. It's an MDS, maximal distance separate. Thank you very much. I keep on calling it maximal distance something. The S is very useful in that sense. So if you have a change, if you change 1 byte in the input to the MDS multiplication, you will affect at least 4 bytes, meaning all bytes at the output. If you change 2, you have to you affect at least 3. If you change 3, you affect at least 2. And if you change 4, well, you may affect only 1, but it's more probable that you affected everything. So this is a very nice thing because modern ciphers are built around the concept of confusion, which is usually the Sboxes, the nonlinear parts, and diffusion, which takes this a bit of nonlinearity and spreads it all around. Now, in order just to give you the field, if you're interested, it's 11b, x to the 8, and etc. It doesn't really matter. I'm not going to discuss this anywhere in the talk, just for completeness. The Sbox subbytes, you first of all invert the input over the same field, where we define 0 to b itself inverse. Then you compute this nice matrix over GF2 and add this nice vector. Now this is a very nice Sbox because it has very, very nice differential properties. Specifically, you get something which is as uniform as you can get for differences for the differentials. Okay, sorry. Difference distribution table is a prediction saying, given some input difference, what is going to be the output difference? And there are probabilities associated with it because this is not, when you look at differences, you lose some determinism in that sense that the difference 1 can be either between the pair of values 0 and 1, but it can be between the pair 2 and 3, or between 4 and 5. So when you have something like that, you don't know actually what was the pair. And this is actually how the key affects differential cryptanalysis, because it actually selects which of the pairs with input difference 1 was entered. But there are 128 such pairs, and the difference distribution table, which is a sort of a prediction, just a probability distribution. If you have an input difference 1, the output difference is going to be 3 with probability either 0, 2 to the minus 7, or 2 to the minus 6. This is the case for the Sbox that is written here. And specifically, this is the best that you can get with an 8-bit to 8-bit Sbox. There is one entry of 2 to the minus 6 and 126 entries with probability 2 to the minus 7, and all the rest is a 0, given an input difference. So it's a very nice Sbox. Okay, the key schedule algorithm, you first of all put the key in a 4x8 matrix. Now you work on all words, all columns of 32 bits or 4 bytes. So the first column, you take these two things. So first you rotate this column a bit, and you put it through the Sbox and generate this new byte. The last byte is affected by also some round constants to prevent this structure to be too self-similar. We have attacks that are based on such things. So this is how it works. The next column is generated by a simple XOR of two columns, simple XOR, and then again we have an Sbox layer, this time without rotation, and then XOR, and then another 3 rounds of simple things. Now the reason for making this thing only use the Sbox every 4 words is efficiency. No other reason behind it. Besides that, sorry. Okay. So, as I said before, these Sboxes are really, really nice. They have very good differential properties. The mixed column operations, because it's an MDS matrix, make sure that you have a diffusion from 1 byte to the entire column. And when you take into consideration the fact that there is a shift rows operation, if you change even single bit of the plain text, after 2 rounds, you may affect all the bits of the internal state. This is a very strong property, and it's actually a very good property. It was designed using some sort of thing called the wide trail strategy, which assures that the number of active Sboxes, okay, an active Sbox is an Sbox with non-zero input difference. When there is a 0 input difference, there is a 0 output difference with probability 1. When you have a non-zero input difference, you have some distribution on the output difference. So an active Sbox is an Sbox with probability associated with the transitions. So we would prefer to have as few active Sboxes as possible. And specifically, in the case of AES, you can show that if you have 2 rounds, the minimal number of active Sboxes is 5. For 3 rounds, it's 9. And for 4 rounds, it's 25. Now, the probability of each transition is at most 2 to the minus 6. Assuming independence between the transitions, which is not necessarily the case, the probability for any 4-round differential characteristic, every prediction of saying this input difference became this input difference after 1 round, became this output difference after 2 rounds, after 4 rounds, will have probability of at most 2 to the minus 150. Now, the state is it's 128 bits. Meaning that you have 2 to the 127 pairs. If you take 2 to the 127 pairs, each of them satisfies the differential characteristic with probability 2 to the minus 150, the amount of pairs satisfying all the differential transitions is going to be less than 1. Meaning the probability of finding a pair which satisfies this differential characteristic is negligible. Okay. There are some other 4-round assurances. For example, after 4 rounds, there are no more impossible differentials, and there are no 4-round square properties. More than 4 rounds. 5 rounds is the... Now, the thing is that I'm saying it was believed that AES is secure because there are no good differential characteristics. You start with some input difference. For any transitions, for any set of transitions, the probability of finding something good is very small. Now, the thing is that actually in differential cryptanalysis, we do not care usually about the exact path. What were the transition differences? We care only about the input and the output differences. And this is mostly because of the way the attacks work. You take many pairs and you find the pairs which satisfy some input and output difference. You don't go over after all the things in the middle. So there is a concept called differential, which is actually saying what's the probability that a given input difference will become some output difference independent of the transitions in the middle. So it might be the case that each path has a very low probability, but the total probability of an input-output difference pair is much higher. So there was a series of papers that actually showed that 4-round AES has no differentials, meaning there is no input-output pair, input difference-output difference, pair, which holds with probability of 2 to the minus 110, meaning that you still need huge amounts of data just to break 4 rounds of AES. And that's why differential cryptanalysis will not work on AES, and the same goes for linear cryptanalysis, which is another flavor of cryptanalysis based on approximating the encryption by using some sort of a set of equations with some error margins. Okay. So hopefully by now you're convinced that AES is secure. Right? AES is secure. I mean, NIST had to pick a good cipher. And they looked at the 5 finalists, and they said, well, we don't like Bruce. Sorry, I'm kidding.
Serpent's too slow.
Serpent is too slow. Mars is too complicated. If we will pick 2 fish, the harder people are going to kill us. RC6, well, there is a multiplication. The harder people will not really like it. Rivest has too much money anyway, so we don't have to give him any more honor. Yeah, let's pick Randall. Now, they had to do so very, they had to do it very delicately, and they had to make sure that it's secure. And people try to attack AES, and with the wide trail strategy, people had very good feeling about the security of the AES. So it's actually secure, sort of. We'll see in a second. So, how did we get here? I'm sorry. Yeah. Okay. So here's a bit of an overview of what happened in cryptanalysis over the years. Now, in the early 80s, when cryptanalysis just became academic research field, people looked at ciphers and said, here is a cipher. They twiddle bit number 5 and see what happens in the ciphertext. They would do experiments like that. They would take an encryption function, they flip a bit, and they wait to see how many times the output of bit, let's say, how many times when you flip bit 5, bit 6 of the ciphertext is flipped. Then you had a very nice set of criteria, like the avalanche criteria, the strict avalanche criteria, all these things which were actually statistical properties, which nobody really knew why they are there. But if you succeeded to find one of these, you would break the scheme. Now, they're using statistical tests. So they took a small data set, because this is before the time that most people had access to computers. And actually exporting code that does cryptography was a bit hard. So you had to write everything on your own, on your VAX, whatever that you had in your university. Sorry?
780.
Well, depending on your university. You were lucky you had 780. And the poor bastards who had to work with punch cards. At the beginning of the 80s, it was a bit out of the place, but anyway. So people actually went and tried it and measured and said, okay, 60% of the time bit number 1 is flipped, so there is some statistical impurity, and people actually verified these results, and people worked very hard. At some point along the way, we started to understand how things work. So around mid-80s, people started to say, there is an attack. I didn't verify it explicitly, but I can tell you, I can prove to you that it works. Let's say meet-in-the-middle attacks. We understood the concept of these attacks. We know how they work. So instead of telling you, I actually went and did the meet-in-the-middle attack and computed 2 to the 50 steps, there's a very nice paper by Schaumann Evertse from Crypto 85, finding meet-in-the-middle properties, meet-in-the-middle attacks on reduced round DES. And the last attack is on 7 round DES, rounds 2 to 8, with complexity 2 to the 52. I can assure you, I can guarantee 100% that they didn't actually verify it. But we all know that the attack works. And why we know that it works? Well, it's very simple. We understand the theory behind how the attack works. We understand the property. We came to an understanding how the things work, how it affects the security. So you don't actually have to do the experiments, you just have to find the algorithm and convince you that the theory behind it works. Now, at that point of time, people have started to assume that 1,000 known plaintext is okay. As an adversary, obtaining 1,000 known plaintext is a legitimate requirement, and the time complexity had to be much lower than exhaustive search. This was the breaking point. Your cipher is broken if by taking 1,000 known plaintext, I can run for something which is faster than exhaustive search. And then came 1991, where differential cryptanalysis was introduced. Now, besides the fact that this was the first attack on the data encryption standard, which was faster than exhaustive search to some sense, it had broken one barrier that we had. First of all, chosen plaintexts are okay. I mean, before that, people said, okay, if you have 1, 2, 3 chosen plaintexts, it's okay. But having real amount of data complexity, 2 to the 47 data. And I think that when Don Coppersmith had to sort of defend the data encryption standard, he said, well, doing 2 to the 56 encryptions in your garage is much faster than obtaining 2 to the 47 data in a chosen plaintext manner. So people would still prefer to use exhaustive search over differential cryptanalysis to break ciphers, but suddenly in the academic circles, it's okay that you require 2 to the 47 chosen plaintexts. Okay. In 92-93, the related key attacks came into play, which is even crazier. I mean, let's look at known plaintext. I have some standard. I'm encrypting data. I have to encrypt the header according to some standard, so I know what is encrypted and I know the ciphertext. Then came chosen plaintext. Well, John, please encrypt this data so I could break your scheme. Now came the related key approach, which says, please encrypt this data under this key that I don't know. Now flip bit 5 of the key. Don't tell me what was the bit, and encrypt this data. Now this sounds a bit crazy. How dare we tell the person that we are going to attack, listen, it's very nice of you that you encrypted me 2 to the 47 data. I just need you to flip these bits of the key or rotating the key a bit and encrypting another 2 to the 47 data. Wow, we became very, very cheeky people. Yeah. Yes, I will discuss it a bit later, but there are natural relations. And specifically, the paper from 93, there were 2 papers actually that introduced related key attacks. The one by Knudsen from 92, and the independent paper by Bian from 93. And he actually showed a related key attack with rotation relations, which uses Oracle access to encryption with 1 key, even though it's a related key attack. It was a sort of a defining complementation properties based on rotations. But still, it's a related key attack. It uses rotations, but in access to the Oracle with only 1 key. The field becomes crazier as time goes by. Now, if you're used to, let's say, public key cryptosystems, I mean, yeah, known data, chosen data, who cares? Related key attacks, okay, so 1 out of 5 times that you generate keys, you will have issues. Well, depending on the probabilities and all that stuff, but even related key is something that you can live in the public key cryptosystems. And then came the 97 competition, the AES competition, where people started to be very paranoid. 1 strike and you're out. There is some statistical impurity with probability 2 to the minus whatever. 2 to the minus 110, you're out of the game. Now this is a very strict approach, and it has very good reasons. I will discuss it in a second. Then came 99, and then we started to have adaptive chosen plaintext and ciphertext attacks in symmetric key cryptosystems. Again, the models get crazier and crazier. Now if you're from public key cryptosystems, who cares? I have this, I mean, if you discuss CCA2 security, this is the main problem of public key cryptosystems. because, well, the adversary can generate adaptive queries. In block ciphers, it sounds a bit crazy. So, as you can see, slowly we became from a field of people doing practical stuff to a field of people who do the following crazy things. And this is a quote from one of my papers. Don't take the CV too seriously. So, time complexity of a related key attack, the total time complexity of step 2b, which was the dominating part of the attack, is 2 to the 423 SHA-1 encryptions. Yeah. The data complexity, by the way, I didn't write it down here, but it's about 2 to the 160 related key chosen plaintexts under 4 related keys. And as you can see, 2 to the 420 is a very practical thing. Okay, so I'm cheating, right? The thing is, the key size of SHA-1 is 512 bits. Meaning that as an adversary, if I'm limiting your time complexity to only 2 to the 423, you will use my attack. You will not use exhaustive search, because it will take you a bit more time. Of course, you will not use my attack because the data complexity is a bit high and just the time required for transmitting all the data. But this is something else. This is one of the good things about academia. You can do whatever you want. And so most of the cryptanalytic papers today actually discuss what we call certificational attacks. So the data complexity is just slightly less than the entire codebook. And actually, I have a paper which uses more than the entire codebook. FSC 2007 or 8. Very nice paper, by the way. Seriously, the concepts are nice. The fact that you need more data than there is. Actually, we use there several keys, so it's okay. The time complexity just slightly less than exhaustive search. And memory, well, nobody cares about memory complexity too much. I mean, you just need to store the data. Of course, the memory complexity has to be lower than the time complexity because you have to initialize the memory. And nobody really cares if it's a fast memory like RAM or it's, let's say, hard disk or something. I had once a discussion with some cryptanalyst who suggested the following model to store huge amounts of data. You send it in a beam to a repeaters in some other galaxy, which sends it back, making sure that it arrives just in time when you need it. Then you don't have to store anything. Okay. So actually, why are these things are still published? I mean, okay, I ridiculed my field. Don't read cryptanalysis papers. They are very boring, very unrealistic. So one reason is that actually, why would you use a primitive which is not optimal? There are more optimal solutions, so pick the ones that do not suffer from these kind of attacks. So if you have to pick between Rindle and Serpent, Serpent has more security margins, more safety margins, sorry. Okay, so pick something which is more secure. Another thing is that actually, if we will publish only papers which have practical attacks, no paper will be published. Well, almost no paper will be published. And the thing is that attacks only get better. So if I will not give you this hint about where there is a problem, and you have a new idea that you didn't thought about that it can help, but somehow it matches the property that I found, and attacks only get better. And you can see it in attacks, for example, on SHA-1. Now the best known attack on SHA-1 in these crazy settings has time complexity of about 2 to the 300, which is still a huge amount, but it's much better than 2 to the 400. So we get better as time goes by. But actually, it doesn't solve our real problems, our core problems, which are answering questions from users of cryptography. Does this attack affect my system? Okay, I mean, at the end, there is a buffer between academia research and everyday life. And in some fields, the buffer is very large. In some fields, it's very small. In the case of cryptography, there are security engineers. And then there is the public, and the security engineers have to answer these questions. And they have no idea. Should I still use, yeah?
I think the user's real question is, does the next attack affect my system? The one that hasn't been published yet. Or it won't be published because the guys in Ukraine are busy making money.
That's true. But the problem is that my crystal ball is not really good today. There are a bit of clouds. Sorry, I'm a bit jet-lagged. All the English that I know went. So I'm terribly sorry for all the mistakes. And actually, this is something that happens a lot. People are still using MD5 for certificates. And
people is us, by the way.
I was trying to avoid saying that out loud. Brian told me yesterday. Now, I'm not even discussing the problem of mitigating problems. This is a real issue. Crypto agility is a real issue. It's not something like, it's very easy to pick at Microsoft or, for that matter, any other company. For it takes you so long to mitigate this problem. But there are good reasons for that. I guess that you know it better than me.
But don't worry about it.
Hmm?
Well, it's only been 6 years since we started working on it. We're still working on it.
6 years is a legitimate time span in... Of course!
Fill the position of MD5 removal program manager.
Yep. So as you probably know, if you're something not related to Microsoft, if you're caught speeding in Australia, you can actually ask your fine to be, well, if you have an automatic camera that takes a picture of you speeding, you can ask the fine to be discharged because they use MD5 for ensuring the authenticity of images that the camera took. It was a real case in court, and the state, instead of calling a real cryptographer, just said, well, MD5 is broken, and therefore the fine is not authentic enough. They discharged the guy. So even let's say, real life implications are very hard to predict. Okay. So what is actually a break? And we have this issue inside the cryptanalysis community as well. And your guess is good as mine. Actually, it's probably better because if you try and think about it from different points of view, from theoretical, practical point of view, anything which is better than exhaustive search is okay. So this is the extreme approach that says the maximum of time, data, and memory is less than exhaustive search. And of course, the data has to be less than the entire codebook. Another approach is that the time, data, and memory is better than generic attacks. So we have meet in the middle, we have time, memory, data trade-off attacks, first introduced by Hellman around the 70s and the beginning of the 80s. And today we have some other variants of it, like the rainbow tables. If your attack is better than these generic attacks, then the cipher is broken. Saying that, at the end, you can break any system with a generic attack. That's the whole point of generic attacks. They work for any block cipher. Now there is a new metric which is promoted by several people, which is time times memory is less than the required for exhaustive search. And the concept behind that is that if you have a memory circuit, memory gate, take the hardware that was used to implement it, transform it into a hardware that does exhaustive search. So if you take 2 to the 100th memory, you can transform it into about 2 to the 90, let's say, 2 to the 100 order of magnitude circuits which do trial encryptions. Of course, this is a bit cheating because it depends if the memory that you need in your attack is RAM or hard drive or whatever, which makes everything even a bit harder to compute. And of course, the best metric in the real life is money. I'm limiting your time. I want to find the key in a year. How much money it would cost you using this approach, this approach, this approach, and the attack? If the attack is lower than any previous approach, it's a break. So any guess is good. And it depends on the system that you're trying to work with. So let's put this debate behind us. Let's look at practical attacks. Now, let's try to upper bound the complexities of attack so we could consider it to be practical. And I will discuss only time complexity because the moment I'm discussing a time complexity, this is a bound for the data complexity. If you wait 2 to the 56th time to get the encryptions, this is the time. So assuming that the time complexity is always as large as the data complexity, I can discuss only this issue. And of course, this also gives a bound on the memory consumption. So the desk cracker by EFF, the Electronic Frontier Foundation, computed 2 to the 55 desk encryptions in about 56 hours. Today you can do it even faster. You have the Copacabana machine that the Bochum guys built, a very nice FPGA board. You put about 10 or 12 FPGAs, connect it. It's a machine that used to cost 10,000 euros, which is about $50,000 these days. And it found the key of the data encryption standard in about 17 days. So if you want to find the key in less time, you just buy more Copacabanas, assuming the time of a PhD student is 0 when it comes to constant. Now there was the SHA-1 Boeing project, which tried to do 2 to the 61 evaluations of SHA-1. Actually, there are debates if they were trying to do 2 to the 63 or 2 to the 61, but this thing didn't finish. After 2 years of computation, they just stopped the project. They didn't really tell why they did so. So we can guess either there was a problem, they needed more time, or there was a bug in the software. Anything goes. So I think that if you say 2 to the 64 cycles is a practical time complexity, we will all agree on that, right? I mean, yeah.
The NSA and NIST guidelines essentially say 2 to the 80 is good enough for this decade and it's not good enough for next decade.
Yeah. I agree, but the problem is that, I mean, if I will try to convince people, listen, the NSA can read your emails. Their assumption is that the NSA can read their emails anyway.
No, that's their guidance for civilians, so other guys won't read their emails.
Still, the Russians read your email. No offense. Well, maybe not your email, but everybody are reading everybody emails, and especially these days. There was a report recently about the countries which actually participate in cyber warfare. And I think that Russia, China, the US, and I think that another country ranked very high, having not only defense forces, but also offense forces. And I don't have to tell you that North Korea is probably doing such things. And if you're from Estonia, or you know somebody from Estonia, you probably know what happened 2 years ago, I think, a year ago, 2 years ago, when some people at Russia were very pissed off at the Estonians. So let's say 2 to the 56. I mean, if you want to play with this bound a bit, 2 to the 64 cycles, which are about 2 to the 56 AES instructions, AES encryptions, just move the line. It doesn't change anything too much. So here is a summary of attacks on AES-256. So to remind you, AES has 3 variants: 128-bit key, which has 10 rounds, 192, which has 12 rounds, and 256, which has 14 rounds. So this is the number of rounds of the attack. This is the time complexity. This is the practical borderline. This is the exhaustive search, the certificational crazy model. And this is, of course, logarithmic scale, because otherwise we will need a few floors extra. So these are results in the single key model. You can see that the best known attack on up to 8 rounds of AES-256 with access to Oracle, which encrypts under 1 key, takes about 2 to the 149 or something like that. It's a paper by Dmitry and I forgot his name, I'm terribly sorry, from FSC 2008. And the only practical attack on AES-256 is on 6 rounds by Ferguson et al. So go and ask Niels from across the street to discuss this result. In the 2-key model, or in the 4-key model, in the related key model, when the adversary is allowed to probe the oracle under different keys, the best known attack is on up to 10 rounds with time complexity of about 2 to the 170 or 2 to the 173, if I remember correctly. Now this was the case up until recently, and then Dmitry and Alex and Ivica in one of their papers, and Dmitry and Alex proposed 2 attacks on AES-256. The first one from Crypto 2009 takes about 2 to the 135 with encryptions under 2 to the 35 related keys. It's crazy, but it's still better than exhaustive search. And the recent Asia Crypt paper, which Dmitry is going to present next week, is 2 to the 99.5 time complexity and data complexity, and the access is, and you use 4 related keys. So as you can see, attacks only get better.
So somebody was giving a talk about attack on full 10 rounds in Italy. Anna Romoli, I think is her name.
Yeah.
Full 10 round, but I don't know any of the results. Have you heard any of those?
I tried to contact her. So first of all, she claims statistical results on AES-128. As far as I understood from the abstract and from the email that she answered me, was this is a single key model.
Where
But
she didn't give you a time.
didn't give anything. She just said that after her talk, which I think is about Thursday or Friday,
Coming Thursday?
yeah, there is on the 4th of December, I think they have, or either the 3rd or the 4th, they're going to have some sort of crypto day in their university, a symmetric key day in the university. They are going to discuss the security of block ciphers. She will discuss her results, and then she will publish an abstract of her results. Who knows? I just want to, in that line, there was a guy, Claude Gravel, a student of Gilles Bressal, who gave in Crypto 2009, in the RAM session, he spoke about the fact that he found statistical problems in AES. And we actually went and redid all these experiments, and as far as we know, the experiments failed. So he found some artifacts that are caused by random things. He picked some huge amounts of data, it took 4,096 chosen plaintexts, and he said that if you encrypt them, the ciphertext have some problems in the chi-square test, and we found out that it has we are currently running a second simulation, but the first simulation showed that you get such large biases after the amount of random trials that you expect. He claimed that the biases are larger by a factor of 10.
It wasn't even percentages, right? To try to, it wasn't, it was rejected from the round.
He gave a very quick overview of it in the RAM session. He was speaking just before me, so I remember it very clearly. No, and then somebody told me, Adi told me, implement. So it's implemented and it's running. So these are the attacks that represented in the paper. So the first one, for example, is these are attacks, the yellow ones, and I hope that there is no one here who is colorblind. I'm terribly sorry if you are. I will try to. So these two results are in the related key model. And you can see that, for example, you can attack up to 9 rounds with complexity of 2 to the 39. And most of it is data complexity. Once you gather this amount of data, you automatically find the things, and the analysis time is less than 2 to the 32. Meaning that as an adversary, you can sit at home, get the 2 to the 39 data, and then do the analysis in less than a minute. In the related subkey model, which is slightly different, and we'll discuss the differences, you can attack up to 10 rounds with complexity of 2 to the 45, and even 11 rounds in quasi or semi-practical complexity of 2 to the 70. So now it's a bit, well, it depends if you want to put the line here, or if you're NSA or someone else, but these are roughly the time complexity. Sorry?
They all require Oracle, right?
They all require chosen plaintext capabilities or chosen ciphertext capability, and under the related key or the related subkey model. So, of course, we require some knowledge about what's going on, but I will discuss a bit later that it's not as bad as it sounds. Okay. So as I said before, the related key model was introduced by Knudsen and Biam, and around 96, 97, people started to use related key differentials. Now the concept there was to use differences in the key to cancel differences in the differential characteristic. Because you have a key schedule algorithm where differences propagate in some manner, and then they are injected into the encryption process in some locations, and you can actually use these differences to play with things. Now, there is a set of good relations, which we all agree that are good relations, and if you will submit a paper, it will get accepted and that sort of stuff. So if you have XORs, rotations, or additions, there are legitimate requirements. Legitimate relations. Now, if you have AND or the use of XORs and additions together, people tend to be very unsupportive of your paper. And the reason for that is that if I give you a related key, encryption under key K, and encryption under key K or 1, I give you access to these two oracles. You can easily find the least significant bit of the key. Encrypt under the first one, encrypt under the second one. If the encryption is the same, then the OR1 didn't change anything in the key. So we know that the least significant bit is 1. Now, there is a guy who presented a paper in workshop on coding and cryptography this year who claimed that he had an attack on all ciphers using related key. Now his relations are good in the sense, there was a theoretical paper by Bellari and Kohono by Yoshi and Mihir from 2003 or 2004 when they showed that the relation has to be bijective in order for everything to be okay. So you can see, for example, that AND OR is not good and XORs and rotations are good relations. Now he showed that the generic attack that works using a very crazy but bijective relation. So this is not something to be afraid of in the practical sense, but from the theoretical point of view, it proves that there is no way to construct a cipher which is secure against related key attacks. And then at the end, it boils down to whether you have this relation in the system that you're using. If you're going to build an Xbox and you're going to defend it using a Merkle-Damgard transformation of the T cipher, which has problems with related key attacks, because you transformed a block cipher into a compression function using the Davis-Mayer mode, you give a very strong hold for the adversary to apply related key attacks. If you have a SCADA system sitting in nowhere, sending data with the key which was embedded into the device, the related key relations are very, very weak. You don't have related key attacks on the sensor there. You might have on the reader at the other end, the receiver at the other end. So it's very tricky, but I'm going to discuss relations which are relatively okay, which are XOR relations. So for example, if you discuss the probability of differential, you can see that you take the probability when you pick a random plaintext, encrypt it under the key, so you give it to the oracle, and you take a plaintext with some plaintext difference, and you ask what's the probability of getting some specific ciphertext difference. So for round AES, the probability here is bounded by 2 to the minus 110. In related key differentials, we have encryption of P under the key K and encryption of P XOR delta P under the key K XOR delta K. And these probabilities tend to be very different when you allow yourself some key differences. Okay. Now, the related subkey model is a bit crazier. How I define the related key, let's say relation which is an XOR. You take the key, you XOR it with some constant, and you ask for the encryption under the XORed key. Now, you can say, listen, this is a bit crazy. But reality shows that there are protocols in which you can do that. There are protocols where you can flip bit number 5 of the key. Real protocols. Now, in the related subkey model, we take a key, K, we look at all the subkeys it generates, XOR subkey 2 and 3, for example, run backwards the key schedule algorithm, find the key that satisfies these subkeys, and then use this key. So this is even a bit crazier. I mean, we don't XOR the key, we XOR subkey and then run backwards. Now, the key that is generated adheres to the key schedule algorithm. It's not a fault attack where you flip bit number 5 of subkey 20 and you don't do anything else. You flip bit 20, you roll back the key schedule to get the new key, and then you generate all the subkeys according to the key schedule algorithm. So it's not a fault attack, and it's something that you have to be very careful. Now, this sounds a bit crazy, and it is. But on the other hand, when you use it in systems, in real systems, for example, if you take AES-256 and you put it as a compression function in a Davis-Mayer mode, you have this capability. An AES-256, like any good block cipher, should be used in a Davis-Mayer transformation of a block cipher into a compression function. And if you do not follow this transformation, it doesn't matter. There is a standard transformation taking a good block cipher, making it into a good compression function. And this transformation allows for related key, related subkey, related whatever capabilities you want. An AES-256, for example, due to these results, cannot be transformed into a secure compression function, meaning that there is a problem with AES-256. Okay.
Sorry.
Yeah.
Is this AES-256 reduced round or the full AES?
So what Dmitry, I guess, is going to talk about it tomorrow is the 2 to the 99.5 attack is for the full AES. We discuss here only the 10 round, just because, well, we try to make the attack practical. If you lose the practicality assumption, then you can do more. Okay. So let's go over our results. So trying to, without entering into the too many dirty details, if you take this key difference, now this is gray, 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 pink, pink. Again, I'm terribly sorry if any of you is colorblind. Gray means that all these 4 bytes have the same difference as these 4 bytes, which is the same as this 4, and these 2 pinks are the same. So if you put this into the key schedule algorithm of AES, 256, you get gray, 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 2 pinks. When you generate this column, you apply Sbox on the shifted or rotated column here. White, by the way, means 0 difference. So no difference in the input, no difference at the output of the Sboxes, and you XOR it with here, so you get gray, and then this column is the XOR of this column and this column, so when you XOR 2 things with the same difference, you get something without difference, etc., 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 until you arrive to this round. These are the same bytes, so this byte is equal to this byte, these are equal. This is something new, this red thing is something new, and then you have here blue, blue with green, where green is the XOR of blue with pink. Yeah, this is not RGB scheme. This is just a nice way to, otherwise it will be right. It will have alpha 0, alpha 1 running around here. You will have alpha, beta. I think we tried to do it with letters. And then at some point we started to look up in the dictionary for more Greek letters. And at some point we said, okay, colors is okay. So what do we do with it? And this is the related key differential that we build with it. So if you start with an input difference all gray and you XOR gray key difference, you have no difference, no difference, no difference. 2 pinks, pinks. These pinks become blue. I'm terribly sorry. Which after the mixed column transformation becomes gray. And then it's cancelled. Now, trust me, it works. But the interesting part here is the fact that you can have 1 round with no active Sboxes. This happens with probability 1. If we had only differentials or differential characteristics, it would be 2 to the minus 6. 2 rounds with only 2 active Sboxes rather than 5. 3 rounds with 1, 2, and that's it. 2 active Sboxes rather than 9. And in total, this entire path has probability of 2 to the minus 56 for 8 rounds. And you can count the number of active Sboxes. This 1, 2, 3, 4, 5, 6, 7, 8, 9 for 8 rounds. The wide trail strategy ensures that you will have at least 50 when you do only standard differential attacks. Now, in our attack, in some of the attacks, we don't care what happens in these 12 bytes. Sorry, this helps us a bit with the probabilities. It increases to 2 to the minus 36. Now, these probabilities, and actually this is something which we always hide, assume that all the transitions are independent. That the probability of the entire transition is the product of all the transitions, the probabilities of all transitions. Now, usually you cannot verify it, but when you have a practical attack, you can. So we looked at the 7-round differential characteristic because the 8th round is a bit harder to verify. So we looked at the first 7 rounds, so stopping everything here. It doesn't matter where you stop it here or here. This transition has no probability associated with it. And we generated the differential characteristic is expected to have probability 2 to the minus 30. So we took each time 2 to the 32 random plaintext pairs, which adhere to the input difference and checked what happens in the output difference. Now in this scenario, because this is a random process and everything, you do not always get 4. Sometimes you get more, sometimes you get less. The number of right pairs which satisfy this entire characteristic, behaves like Poisson with mean value of 4. Trust me, Poisson with mean value of 4. I'm not going to cover this. So you can see that in theory, if we run 100 experiments, we should have expected 1.8 tests with no right pairs. We had 0. 1 right pair is expected in 7.3 of the tests, but we had 10 of these. And you can see that it's relatively okay. I mean, this is not exactly Poisson 4, but if it's Poisson 3.5 or 4.5, we're not going to fight over it. Well, we can, but it's not the point. Yes?
What's chi-squared?
Poisson 4.
I think that in this case, you shouldn't see any problem. It should be the same. But, you know, they say should is the name of a fish. In Hebrew, should, the word for should, amur, is a name of a fish. It's a type of a carp fish. So we haven't done this experiment. Actually, I would run it afterwards. So in the related subkey model, what you do is you shift all the differences one round. Now, usually when you shift differences one round, it has no effect. But when you have related keys thrown in, then the key schedule behaves slightly differently. So that's why we needed the related subkey assumption. So we push everything 1 round forward or 2 rounds forward, depending on the exact attack, and then let the related subkey assumption take care of the issues that form because of the slightly different locations. But all in all, the attack is the same. I mean, if I show you this related key differential to Cryptanalysis, you would say, okay, take 2 to the 36 pairs. For example, you start with 2 to the 36 pairs. You expect to get 1 right pair with this difference. When you find this pair, you know that some things happened, and you can use this to find the key. So, starting from here, it's a very standard transformation. It's not like I'm omitting some stuff, but it's not important. Now, we also looked at another attack scenario where the plaintexts are not generated as random plaintexts. Usually chosen plaintext assume that the adversary chooses a plaintext at random and then plaintext X or something, because we need to get randomness from somewhere. This is the true reason for picking plaintext at random. Now, we decided to look at counter mode. So counter mode is a way to transform a block cipher into a stream cipher. You initialize a plaintext, which is some IV and a counter. You encrypt it under the key, and then you XOR the outcome with the plaintext you're trying to encrypt. You increment the counter, and you do it again and again and again. So we said, let's assume we have such a system. The plaintexts are not generated. Actually, the attack goes after the stream, not after the plaintext, but after the stream that was generated, in a very non-random way, very deterministic way. Is the attack still works? And actually, we did the experiment, and it works. The same distribution, everything is the same. So if you have a counter mode embedded in some system, you let it run. Now, we take it, we reinitialize, we have to change the key. This is a related key attack. We have to change the IV at some point, and change the counter, and let it run as well. And if you do it correctly, the attack works. We actually verified it. Now, we also did some attacks when we say, okay, let's assume that we use ECB. Shh, it's a bad way. And we restrict ourselves to cases where all the plaintexts are ASCII characters. And the attack still works. The differential still holds. The probabilities work. We also discussed the case where actually the ASCII characters are numeric values. So we have a database encrypting only numbers. And the differentials, because they are what they are, still works. So if you're going to have some security engineer saying, I want to use AES-128 because it's really, really fast, and I want to make it more secure by extending the key schedule algorithm from AES-128 to AES-256, 256-bit key is better than 128, and the speed of AES-128 is still better. So if you take AES-128 and you fortify it, you actually completely crash the security in the related key model. I have to be honest, it's in the related key model. Now, the minimal Hamming weight of the key difference is 24. Now, this is important if you're hardware people and you take a device and you start hitting it until the key flips in the right positions. So the minimal Hamming weight of the key differences that we need is 24. But we didn't try to optimize this a bit too much, so I guess that you can actually improve this a bit. But it's not a real issue, I think. Okay. So this is a summary of the attacks. You can see whether it's a key difference or a subkey difference or related key or related subkey. If it's a distinguisher, or you can retrieve some bits of the key or the full key. For example, the 9 rounds related key attack takes 2 to the 39 time, 2 to the 39 data, and 2 to the 32 memory. Well, yeah.
So going back to the Meyer application, so I see you get like these subkey bits. Have you thought about what that translates into in Davies-Meyer application for getting collisions?
Yeah, you can actually. There is a set of differentials which start with 0 difference and ends with 0 difference. Yeah. Yeah, but you still need to do some. So what happens is that, for example, if you skip this round, you start here, so with 0 difference here, and you stop here, for example, you have 0 difference. Now, I'm cheating a bit because there are more rounds, but then this differential was optimized for probability, not for finding collisions. Dmitry did the work with finding collisions. He found collisions. I think in the crypto paper or in the AsiaCrypt paper, there is a collision for 13 round AES-256 in Davis-Meyer mode.
Is that on the IACR?
I think it's in both are on the IACR ePrint. So you can do really fun stuff when you allow yourself crazy models. Okay, so can I take a bit more of your time?
Yeah.
Okay, great. So what are the security implications? Because at the end you will have to answer questions from users like, does this affect my system? So, for example, if you extend AES-128 to 256-bit key, actually you lose security. And the real issue, I think, is the fact that the security margins of AES-256 are much smaller than what we expected. AES-256, AES-128, AES-192 were all designed to be secure against related key attacks. Unfortunately, the two latter, the 192 and 256, are not secure enough. Now, if you ask me if NIST is going to change anything, the probability of NIST modifying the AES specifications is, well, like the probability that tomorrow I will visit the moon. And the reason for that is that AES was actually widely deployed. Unlike the SHA-1, MD5, SHA-2 situation, where everybody are trying not to mitigate to something new, AES was very quickly adopted, and there are many products using AES, there are low-end devices using AES. AES succeeded so well that if somebody is going to transform AES today to something else, it won't happen. Now, you can change, for example, the key schedule algorithm.
Yeah, that'd be the easiest way to do it, right? Just make a messy key schedule.
Yes, but the problem is that when you make such things, first of all, you don't know what new problems you introduce. But the real issue is that you cannot change it because there are so many devices around the world, and I'm not talking even about the software implementations. There are so many hardware implementations that you cannot change back. That's it. We're going to be with AES for a very long time. And this is very unlikely to start any AES-2 competition, saying, okay, AES was not good, we have to start again. But this won't happen, because currently they have the SHA-3 competition. And my feeling is that they would rather to roll back time and not have this competition, rather than...
You think they'd rather not have the SHA competition?
I think it causes them more headache than they expected. They got 51 submissions, proper and complete submissions, and now they have to fight with everybody, and nobody likes them because his hash function was not selected. And even I have issues with them because I had 2 submissions and one of them didn't pass to the second round. I mean, it was a good one. I'm not discussing the one that did pass. Of course it's great, but the one that didn't pass, it should have.
Pass the one with the AES permit?
Yes. Of course, the one based on AES round, and now everybody are a bit... So now there is a question, how this will affect the NIST competition. If you're an AES-based, do you have greater chances or lower chances? Now, of course, nobody used the key schedule algorithm of AES. AES-based means that we took the AES round, we stuck it in several locations, and said, okay, we use it as a nonlinear operation. And the reason for that, one of the reasons for that is reuse of hardware and software. The fact that Intel and soon later AMD is going to introduce the AES instruction. So you can do one AES round in 6 cycles. This is the most diffusion confusion pair cycles that you can think of. Yes?
Going back to the key schedule. So you found this brilliant, set of differences in probability 1. Could you share how you found those and if there's more lurking? Is this optimal?
So I was looking at the key schedule algorithm of AES-256 since 2004 actually. So we had some paper about related key differential boomerang, never mind. Some sort of an attack. And we were optimizing to have very good differential characteristics, and we assumed that in order to have that, you have to have minimal number of active S-boxes in the state. So we did everything we could to make sure that the number of active S-boxes locally was optimal, and we missed the big picture. And then Dmitry came with his papers about the full AES-256. And then we saw that there is a different way to deal with that, which pays more in the number of active S-boxes locally, but globally you gain a lot. Sorry, now I think that he has an automated tool for finding best differential characteristics, related key differential characteristics of up to X rounds. But we did this by hand, so very old-fashioned sort of an approach to. But the thing is that I don't believe we try to look. I know that Dmitry ran his tool, so I know that there aren't that the tool can find. But we needed some a change in the state of mind, trying to optimize globally rather than locally, and there was a change in the state of mind. When you try to actually, we tried other things. We actually tried other things, having pink 1 and pink 2, it doesn't work. But I'm not going to commit to the fact that this is the best thing you can find, because I'm sure, 99.5% sure, that if you do something else, you slightly change the model, you push the related subkey model even further. You say, I take wiki classes, so classes of wikis under the related subkey model, you can find something which is even stronger. I'm sure it's lurking around somewhere, but we didn't do it that far because I think that it would take time for the community to understand that the related subkey model is legitimate. Personally, I'm not still 100% confident it's legitimate. It's legitimate in some senses, it's still weird in some other. Okay. Okay, so did we break the full AES with practical complexity? The answer is, of course, no. And should users be worried? And I think that users should be worried, but I would advise against panicking. I mean, don't phase out AES-256 yet. But if you're already running over the code and making sure that you can change the hash function from MD5 to something else, think about putting the hooks to change AES to something else in the distant future. That's it. And the paper is on ePrint.
I asked this question a few months ago, and I got a consistent answer. I'm wondering if it's still consistent now. If you have your choice in practice, AES-128 or 256?
256.
Okay.
Any day. But this is as long as we're not discussing a compression function. This is only if we discuss encryption, counter mode, or elephant, or the real encryption. If you're going to use crazy modes of operation, if you have tweakable block ciphers, and actually some of the tweakable block ciphers assume that you can put a public tweak which changes the key schedule algorithm, and they just introduced related key attacks without, usually when you start a paper with related key attacks, you have to give examples saying related key attacks are very important because the Xbox, because whatever. Now, if you have tweakable block ciphers where people are allowed to change the key schedule from the distance with a public parameter, the related key model seems a bit more practical. So, as long as you're discussing classical mode of operation, no tweakable block ciphers, nothing else, AES-256. Compression functions, tweakable block ciphers, anything else, AES-128.
Okay, so Or is actually here all week until Friday, and if anyone would like to go to lunch now with Or and continue discussion, please let me know. Let's thank Or again.